So, good afternoon, students. So, in the previous classes, we have started on the continuous system vibrations. Till now, we have covered beam eigenvalue problem formulation. We have not solved that eigenvalue problem. Initially, we derived the equation of motion for Timoshenko beam, but we then simplified that by ignoring the rotary inertia and shear deformation. So this is called Euler-Bernoulli beam hypothesis. So eigenvalue problem we already formulated, and we got that is a differential equation of the ordinary differential equation we got in the last class. Also, we introduced the general notation for the eigenvalue problem using L operator and M operator and associated boundary condition in the form of capital B and capital C operators. Those operators in the continuous systems will be differential equations. They will be ordinary differential equations. And then we saw some general property of these operators like self-adjointness, which is related with the discrete system, the symmetry of the matrices, mass and stiffness symmetry. So similar to that, we have here L and M operator, and their property is self-adjointness. And if it is, and even we have seen the positive and positive definite these operators, but till now we have talked these in the general sense. Still now we have not solved the eigenvalue problem for these cases. So today I will take up another kind of vibrating element, that is strings or cables, and initially we'll derive the equation of motion for that, which is much simpler as compared to the beam case, and then we will go for the eigenvalue problem solution for that also. So let us see the slides. So we have, so we'll be talking about the vibration of strings or cables. The application of that are so many. One of the example is here given. The bridges, nowadays they're hanging on the cables, and when the vehicle moves on these bridges, definitely there is a movement of these bridges, and the cable vibrates because of that. So if the resonance conditions is built, then these cables may fail. So during design, we need to ensure that whatever the vehicle moment we are talking about, that should not give the resonance to this cable structure. So we will analyze this cable, how they give vibrations to the bridges or any other structure. So we are talking about vibration of string, in which we know that there is a continuous system, and because of the weight of the string is appreciable. So this can be considered as a continuous system, and the transverse flexibility of this particular cable is negligible if there is no tension in the cable. So the initial tension must be there in the cable so that it can have transverse flexibility. So even we are talking about the axial tension of the cable, they are constant. The vibration take place because of the transverse load onto the cable or the supporting structure, and because of that the cable vibrates and the associated supporting structure also vibrate. So the bending stiffness of this comes because of the initial tension. And I'll just repeat this so that continuity is there. I have taken a small segment of the cable, and this is the transverse load per unit length. This is the load, or this is the deflection of the cable. The length of the cable is small, dx. The tension in the left side is Tx on the cable, which is along the cable, because the slope due to the deformation of the cable at two ends are different. So here the slope is dy by dx. And when we are going through the right side, because the loading is there, so not only the initial tension is changing, this is the change in the initial tension, and this is the change in the slope of the cable. Now, because the loading is in the transverse direction, time-dependent loading, it will this force component which are the transfers to the cable, we need to consider for the dynamics of this particular cable. So if we take the force component of this along the perpendicular direction, that is y direction. So as because this angle is small, so sine theta of this component will give us the force component in the y direction, and theta is angle, this angle. For a small angle, we can consider this as angle, directly angle. So this is the force in the right direction, and this is the corresponding slope angle, which is the sine component, this component. This force into the length of the segment of the cable will give the force in the y direction, and this is in the left side, because the component of that in the vertical direction will be in negative direction. So this will be Tx and this angle. That will be equal to the mass. So this is mass per unit length. So if you multiply by the length, this will be the mass of the small cable, and this is the linear acceleration in the y direction. So this is nothing but the sum of forces onto the cable in y direction is equal to inertia of the cable in that direction. So this is the Newton's second law we applied here, and now we'll expand this equation. So this equation is same as the previous one. Now if we multiply this, we'll get 4 terms, 1, 2, 3 and 4 terms from this, and the rest 3 terms are these. So if you see, the 2 terms are getting cancelled. So this term and this term is getting cancelled, and this term is having dx square term. So dx is small, square of that will be further small, so we are ignoring this small term. And these 2 terms which are put in the box can be combined. How they can be combined? We can combine that like this. So that means if we take the derivative of this, you will get these 2 terms, because both t and this is function of x. So if you differentiate, I will get 2 terms. So I can get back these 2 expanded form of this. So this cancelled, this we have written in this form. This is negligible, and the external force that is there, dx is common, so that can be taken out from the equation of motion. And right side is this inertia force. Dx is common, so this has been removed from here. Now, because at present we are interested in the eigenvalue problem, free vibration problem, so we'll ignore the external force. So if we ignore the external force, we'll get the equation like this. This is the initial tension. This is the mass per unit length. So this equation is the governing equation or the equation of motion of the string, and this is, you can see, is a partial differential equation, but much simpler as compared to the beam case. In beam case, it was derivative was with respect to x fourth order, but here it is now second order. So it is much simpler as compared to the previous one. This time derivative is remain same because this is coming from the acceleration of the cable. So here we can have boundary conditions. Here, if you remember, I obtained this using Newton's law. So once I'm obtaining the equation of motion using Newton's law, boundary condition will not come from the formulation. That we need to consider separately, the physical consideration we need to take. So like if this is the cable, let us say is fixed at this end and is free at other end. So what are the boundary conditions for this? So here, because this is fixed, so we are talking about the transverse vibration. That means vibration perpendicular to the cable. So here the vibration will be 0 at x is equal to 0. Here it is free to vibrate the transverse direction. So if once it is free, so it cannot take any axial load from the support, because there is no support. So there is no reaction force here, because we are talking about the free vibration. So we are not talking about any external force. So we are talking about the reaction force here. So this is that particular component of the tension in the transverse direction. This will be 0. So at the free end, this component should be 0. Tension will be there in between because of the weight or whatever, but here it will be 0. Like if it is hanging, so maximum tension will be here, and because of the weight, and as we go along at free end, there will not be any tension in the string. So there is no force component also in the transverse direction because of the this load. There is one example I have given. So this is one kind of boundary condition in which we can have one end fixed, another free, but we can have other kind of boundary condition in which maybe both hands are fixed. That is also possible, or both hands are free. That is also possible. So now we'll convert this partial differential equation to eigenvalue problem by separation of variable method. So we'll assume the solution like this, in which we are separating the function which is function of x and time. This is the separation of variable method. So if we substitute this in the previous equation of motion, this is the previous equation of motion we have substituted. So because this is the x differentiation, so y will be here, ft will come out from this. On the right side, we had the differentiation with respect to time. So ft will be differentiated, but x will be outside. Now this equation will separate the time-dependent terms in the one side and all the x-dependent term in the left side. And as we did for the beam case, because in the left side and right side, only spatial coordinate terms are there. In the right side, we have only time-dependent component. Like if we bring that t this side, then they will be equal only when both are equal to some constant, and that will be a negative constant. I think this should be 0. This will not come. So if we equate to negative quantity, we'll get this this as harmonic function. So that will give us the harmonic motion. And when we equate the x dependent terms to the omega minus of omega, we'll get this. So minus, I'm taking this side. So if you see the form of this equation, now it is a ordinary differential equation. And once it is ordinary differential equation, the form of the equation is similar to what we're in the beam case, but only thing, the order of differentiation is different. Here, as I discussed in the previous slide, the boundary condition which we had, now based on the solution assumed, the homogeneous boundary conditions will be of the same case. Y is at x is equal to 0 will be 0, and this at x is equal to L will be 0. This is the component of the tension in the transverse direction of the cable. And so this equation, which is eigenvalue problem, associated boundary conditions are there. So it is a very famous problem. This is called Sturm-Lowry problem, which is eigenvalue problem. In literature, this particular eigenvalue problem is referred as Sturm-Lowry problem because these two people, they formulated this eigenvalue problem. Now we'll go back to our general formulation of the eigenvalue problem, which we discussed in the last class. So L operator W is equal to lambda M operator W. Here M is not an operator, just a function of X. And this is the associated boundary condition in which the right side is 0. There is no eigenvalue in the boundary condition. So here also you can see there is no eigenvalue in the boundary condition. So the cable vibration is following in this particular general formulation, where the L operator now will be this. So if we compare the previous equation, this, if we take out the Y from here, this is the L operator. So this is the L operator and this is the M operator. Lambda is omega square. So this is the L operator including minus here. M is this only the function of X, and lambda is omega square. If you compare this and the previous one. Here the order of differentiation of the L operator is 2. So that means 2p, which is in general formulation, we said 2p is the L operator differentiation. So in this string case, this is equal to 2. So that means p is equal to 1. Here is M is not an operator. So q is 0. Okay, this is only function of X. So that means at each boundary, we'll be having p number of boundary condition. So if you are saying X is equal to 0, so here only one boundary condition will be there because p is equal to 1. In the beam case, we had p is equal to 2. So we had two boundary condition at one end of the beam. But now here, because of the L operator, only one boundary condition is there at every boundary. So X is equal to 0. If for the previous problem case, this will be 0. At X is equal to L, this component is 0. So here also only one boundary condition is there because P is equal to 1. As compared to this general formulation, here B1 is 0 because the operator BI is not there. So BI is 0. Basically, it is defining the operator order. So because of this is just function, so operator is 0. But here, if you see, the operator is, if you remove the Y, operator is the remaining thing, which is the B1 operator. So at X is equal to 0, B1 is 0, but X is equal to L, B1 is this operator. So as I mentioned, the number of boundary conditions at each end is equal to P. So here also 1 and here also 1. So this is consistent with our general notation of the eigenvalue problem. Now, as I mentioned in the previous case, I obtained the equation of motion using the Newton's law. But here main focus is to represent the energy and then use Hamilton principle. So I'm just deriving the potential energy and the kinetic energy for the cable, and the equation of motion and also the boundary condition we can able to get from the Hamilton principle. So now if this is the cable, segment of the cable, let us say the length of the cable is ds along this. Along the x-axis, that is small dx, and this is dy. Let us say the tension is T and T plus D. This should be delta capital T. Now, ds can be expressed as square of this, and square root like this, because they are forming a triangle. If I take out the ds outside, this will be 1 plus this. And because there is a square root, so this can be approximated as using expansion. If we write half here, so this can be expanded like this can be simplified like this. There can be higher order terms which we are neglecting. So basically here we are doing the expansion of this particular term. So only the first term we have retained, other we have ignored. Then if we take the dx, if I multiply dx inside and bring that in the left side, so ds minus dx and the remaining term. And now I'm bringing the dx also in the denominator. So ds minus dx by dx. So ds is the, so this is the change in the length, and this is the original length. So this is basically strain in the cable, so which is expressed like this. This is the strain in the cable. Now the strain energy is defined as the force into the displacement of the cable. So for a small segment, this is the force which is applied, and strain multiplied by dx is the deformation. Strain multiplied by the length of this segment is deformation. So if we substitute the strain from here, we'll get this. And if you want the strain energy in the whole cable from 0 to L length, so we can integrate this quantity from 0 to L. So we will get the strain energy like this. So that will be half 0 to L, T is the initial tension, slope square dx. So this is the potential energy in the cable. Kinetic energy can be written as half. This is the, if rho is density, then rho into A. So this is the density. So rho into A is the mass per unit length. And if you multiply by the dx, that will be the length of the cable. And this is the velocity square. So this is the kinetic energy for the whole system when we integrate from 0 to L. So we have potential energy and the kinetic energy. Using Hamilton principle, here only one independent variable y is there. So we can use Hamilton principle, obtain the equation of motion as we did for the beam case, which was much complex. We'll get the same equation of motion as we obtained this one. And even the boundary conditions also will be getting from the Hamilton principle. So this I am leaving it to you to derive and check. So now I'm coming to the solution of the eigenvalue problem for one specific case in which, let us say, the string or the cable is fixed at both ends. So because of the, now we are analyzing the free vibration, and is having some initial tension and we want to analyze the free vibration of this. So in this particular case, the tension is constant throughout the cable. Even the mass per unit length or the mass, this is the mass per unit length. Only rho is the mass density, but once I written rho x, that means mass per unit length is constant because it's uniform. So this equation of motion or this eigenvalue problem will, because this is function of, it's not function of x, so this will come out. So this is that, and I have divided by tension, so that has come to the here beta. Beta is defined like this. So omega square rho by tension I have written as beta square. This is one parameter which has been defined here. So this eigenvalue problem will come to this minus sign will take, we have taken the both terms in the one side, so minus sign is not there now. So boundary condition is in this case x at x is equal to 0, this y is 0. At x is equal to L, other end also is 0. So this is the boundary condition. So this is the differential equation and associated boundary condition. In this case, because this is a second order differential equation, we can have two solution and two the constants C1 and C2. So this is the general solution for that. C1 sine beta x plus cos C2 cos beta x. C1 and C2 we need to find out from the boundary condition of the problem. How we can able to get the C1 and C2? Now boundary condition is this, let us say. So we'll substitute y is x equal to 0 here, x equal to 0 here, x equal to 0 here. So here I have substituted. So this term will become 0, sine 0. Sine 0 will become 0. That means C1 will not be here because this displacement is equal to 0. So only thing will be left out C2. This is also 1. So C2 will be equal to 0. So from the first boundary condition, when we apply on this, we are getting C2 is equal to 0. That means this cos term will not be there in our solution. Now the second boundary condition, this. So in the remaining part, so this is not there, only C1 sine beta x is there. I'm setting x is equal to L. So this is the one. So YL is equal to 0, C1 sine beta L. Now, because these two terms out of this, if C1 is 0, then both C1 and C2 is 0, so there is no motion. So C1 cannot be 0. So that will give us, this term should be 0 to satisfy this boundary condition. So if we equate this equal to 0, this is the frequency equation for the cable case, which is earlier we had in the discrete system, this was a polynomial. Now this is a transcendental equation, sine beta L, and it can have infinite solution. So beta can take various value. So beta L will be R pi, where R can take 1, 2, 3, infinity. Yeah. Only thing R cannot take 0 value, but other from 1 to infinity it can take to satisfy this equation. So it will be having infinite solutions. Now this beta R is related with the frequency of the system. So once we obtain this, because beta is related with omega square, so if we substitute beta R here, omega square can be solved. So omega will be in terms of beta, and beta R we are substituting this, so we'll get this. So the natural frequency of the Rth natural frequency of the system will be R pi under root T rho L square. So the natural frequency will depend upon the tension in the string, mass per unit length, and the length of the cable. So these are the parameter on which the natural frequency will depend. And R is here. So R can take 1, 2, 3, 4. So here, when we take R is equal to 1, we call that as a lowest frequency because others will be higher than that. And that lowest frequency, we call it as a fundamental frequency or fundamental frequency. Here in this particular specific boundary condition of this string, what we are observing that all other R is equal to 2, 3, 4. That means the first, second, third, fourth natural frequency, they're integer multiple of the fundamental natural frequency. So let us say if we are talking about omega 2, that is twice of the omega 1. Omega 3 is thrice of the omega 3 because R is appearing here. So this the omega 2, omega 3, these are called overtones, which are integer multiple of the fundamental frequency are called overtones. And so overtones are also called higher harmonics. Generally, harmonics are we use in the force vibration, but in the natural frequency of the string or the fixed case are happen to be the higher natural frequency or integer multiple of the fundamental. So that's why it is called higher harmonics. Or generally, this will not be the case. The higher natural frequency will be integer multiple of the fundamental or the lowest frequency. Very few cases are there in which this condition is there, and such systems are having the pleasant sound. Like the string which we are talking about, this is used in the guitar also. So when we have the tension in the guitar strings, then if we disturb that string, then we get a sound. So that is a pleasant sound. So because of that, because of these overtones only, we get the pleasant sound. Other structures may not have this kind of behavior of the overtones. So here now you can see the L length of the string is appearing in the natural frequency. So if L is increasing gradually, what will happen? The fundamental natural frequency will decrease. Let us say omega 1 if we are talking about. If L is increasing gradually, omega 1 will be gradually lesser and lesser value will be there. If it is very large, what will happen? Then, and because the overtones, the higher harmonics are also integer multiple of the fundamental one. So all the natural frequency will be coming closer and closer as will increase the length of the string. In a limit, what will happen? They will merge. So all the natural frequency will merge. That means we'll be having continuous frequency spectrum in a limit when length of the cable is infinite. And generally, this kind of continuous frequency spectrum we study in the waves that is not part of this particular course. So I'm leaving this here only. So here we get a continuous frequency spectrum. So every frequency is a natural frequency of the system. So we talked about the frequency. Now what about the eigenvector, which we had in the discrete system, the shape. So shape will be, because now here we got this beta, C2 was 0 here. So Yx can be written as C1, sine beta can be replaced by R pi by L. So this will be the eigenfunction, which is written here. So this is the eigenfunction, which will define the shape of the vibrating body, where AR is the amplitude. So at present it has this, as we know that amplitude is arbitrary in the eigenfunction or the eigenvector. Only the shape is important. And at present this eigenfunction has not been normalized. Generally we normalize with respect to mass. So at present this is not normalized, is as it is. Now I'll take up some property of this operators So I'll just take a 30-second break. Just take a water, then I will start. Okay, I think now this time is almost done, so maybe you can have questions on whatever I covered. And then because this property will take some time to describe. So I'll stop here, but if you have any questions till now, whatever I covered, you can ask. Okay, if you have any questions, please. So even the mode shape today are not shown. In the next class, once I will cover some of the property like self-adjointness. Now we'll see, because we have taken the specific example of the string, we can able to check the self-adjointness property and the positiveness, positive definite, those things we can able to check. And basically, those property gives us the idea about the solution. As we know that semi-definite systems are having one of the zero natural frequency. So, Manpreet, you have some question? Manpreet Singh? Okay, I think by mistake. So I think.
Hello.
Ah.
Yes, sir. Sir, actually, I want to ask that in like continuous system, we have a number of natural frequencies. So all the natural frequency have equal importance, or like first fundamental and the second, these will have major impact.
Generally, the lowest one is the most dangerous. Lowest one is the most dangerous, in the sense that the most of the case the excitation frequency they coincide with the lowest one. The lowest one is having actually the value also low, but if you see in other cases, not in the string case, in other cases the second natural frequency may be 3 times, 4 times more than the first one. So it is unlikely that the second mode or third mode will get excited. Sometime it may be, but not more than third or fourth. And if you're talking about third and fourth, even in that particular case, the nonlinear effect will come, and whatever analysis we are doing, linear analysis may not be valid also. So best example I give regarding the fundamental frequencies, I think you must observe the tempo which you ride. Okay.
Yes, sir.
So when it is stationary, it vibrates more, or when it is running?
Stationary, sir.
Why? It should be opposite, no? When it is running, then it should have more vibration.
Yes, sir.
No, so there is the design so that while running, it should cross the first natural frequency of the system. While stationary, no problem. Okay, it can vibrate. If it is vibrating during running, what will happen? It may topple. Okay.
So we design such like it crosses its first natural frequency.
Yeah, once it is in the motion mode, it is always in the above first natural frequency. Okay, that is the best example I can give.
And higher order does not matter that much.
That will be much higher. That will be, as I told, that will be much higher. Then when you are even going very high speed also, that will be beyond that. So gap between the first and second is usually very large, except in the string case, which is multiple Okay.
Yes, sir.
Yeah.
Okay, sir. Thank you.
Today I shared the video of the lab we have, cantilever beam, vibrations and other things. And that cantilever beam is having first natural frequency around 18 hertz. Second is around 80.
Okay.
So large margin.
Yes,
so,
sir.
Yeah.
And sir, as we said, like as the system is continuous and higher frequency becomes continuous. So
Yes.
in that
So
case means the
the
gap
way,
between these will
yes.
keep on reducing.
So yeah. So it, as I mentioned, okay, if it is infinite, like if you're talking about sea waves,
Yes, sir.
so that can be considered as small infinite body. No.
Okay, sir.
So
Yes, sir.
so there, but those things are the waves. So concept are different. Then we don't talk about the frequency there. There we talk about the wavelength and other things.
Yes, sir. Okay, sir.
No. Yeah.
Yes.
Okay. So tomorrow we have quiz again. I'm announcing that will be 5 to 6 objective type. That will be up to chapter 4 because they're all connected. So and you already read the first 2 chapters. So so from first chapter that it will not be that much, but second, third, and fourth will be the main. Okay, in the this particular quiz. Okay, so I'm stopping here. Have a nice evening.